Okay, section 5. This is where it's starting to get a little bit more esoteric from the last section. Bit more terminology, quite a lot more terminology, but also really thinking about the graphs and how they show on different shapes. There's a great video I'm going to share with you. Watch the video, have a go with the worksheets with it. They're just simple worksheets. Really useful idea. So what we've got two materials going on in this one. We've discussed this before with most groups, maybe not all of them. So again, two ways of looking at this. Maybe for a certain stress, so that's an idea of basically a certain force applied. One of these stretches much more, the strain is much bigger than the other one. So this is your stretchy material, this one is your stiff material. Alternatively, look along here and for the same amount of stretch, okay, same extension, then which one needs more force? That one needs more force. So in our things here, hopefully you will be able to see that quite easily and then go realize that that must be material A and that must be material B. Okay, so two ways of looking at that, as I said in the lesson. Second graph, we're starting to see different materials. Now these materials, assuming they go to the point of breaking, again you've got to read the question to ensure that, because they might just be stretched and then unstretched again. But if they break at those 2 points, then basically this is what's known as a brittle material. There's no yield point as such, it yields and breaks simultaneously, so yields and fractures. This one does yield, it changes shape and you've got that curve and something's going on beyond it. So this one is the opposite of a brittle material. Brittle comes to a point, it might be a big force, it might be a little force, so the stress will vary depending on the materials, but they get to a point, there is no point beyond, so nothing happens here. Effectively, what you need to put in answers and your description is it doesn't have any plastic behaviour, and that's what makes the material brittle. Anything that behaves plastically is the opposite. Even if it's not happening very much, you're going to get a little bit of that. In real life, you might get a little bit beyond, okay, but it will literally be a tiny curve. So, third one, we'll start bringing it back to the idea of energy in that area underneath to get it up to this point, whatever that point is, that will be area worth built up while stretching. That will be the energy being put into the material. And then when we relax it, so unload it, it goes back to this area, and that area is not enclosed. So all of this bit in here is area. This area represents energy that's gone into the material, gone into changing the material itself, bonding energy and things like that. So just to bring everything around, there's a few key phrases again that link in with this, so let's just get some terminology in. UTS is an important one. Just make sure that you use the right phrase, which is nice and easy to start with. Ultimate tensile rather than compressive, because that would be squashing. Not strength, it is stress. Okay, so just make sure we're happy with that one. Obviously, I would hope on these graphs we've got these B's, which all refer to the point at which it breaks, and B just stands for literally breaking point. Okay, so nothing genius there. Okay. The next one, equal dimensions, stretched in the least, low elasticity. That's the material that we know as stiff. Okay, so that is a technical phrase. It is the idea of stiffness, the K value. So I will just put in high value of K. Okay, so even if we keep talking about Young's modulus as we're building up to in the chapter, you can still think of the idea of K, the stiffness from Hooke's law. Okay. Now, if some stretch more and some stretch less, well, the ones that stretch more, copper is a really good one. You can draw them out, you can stretch them, they become very long, thin wires, very much like this, fairly typical, or even D in the middle there. Although that one breaks, so copper goes a long way along. This is basically what we mean by ductile. Okay, so it's that curving section, easily and permanently stretched. Okay, so long thin wires is the clue to that. Now, the materials that do the opposite of this, so the ones which just break, as I say, are brittle. Literally, peanut brittle is brittle. You know what it's like. Cast iron is very similar, so if I was to take one of the masses off here, this is a cast iron kilogram. This is very strong, great, but actually it shatters very easily because it's cast. It's not being machined into shape. It's not been stretched. Okay, it's actually been poured into a cast, hence the writing built into it. So that will be quite brittle. If you drop anything that's been cast iron, it shatters very easily. Okay, so it's this idea of no plastic deformation, no warning sign effectively. Fairly obviously glass shatters because it's a brittle material. So the next few parts are really just, again, use the PowerPoint and go beyond as well. Have a look at the building of the materials. Let's just stretch out. So what do we mean by those? You need to have a really good idea of ductile, brittle, and then polymeric materials. Okay, and those are effectively the three shapes of graphs. So have a look at them. Polymers behave in a certain way. Brittle materials, again, have a look at the idea of what's happening inside. So basically you need simple sentences in here, so write 1 or 2 sentences, bullet points, and then a diagram will be useful. Okay, so do that for each of the three. If you can make a symbolism of what's happening inside, the molecules inside, the slipping of the molecules and so on, that's great. Now, just to bring in one last thing, I've done the notes here for you, but the materials, most materials fall into one of those three properties, okay? Polymeric, brittle, and ductile. So if we start putting them together, if we sandwich them together, we can make composite materials, things like fiberglass. You have a resin with glass in. The glass is very strong, but it's obviously brittle. So you put the resin in, which does the opposite. Carbon fiber is carbon resin around fibers. Concrete, reinforced with steel. The steel is very strong in length. When you stretch it along its length, concrete shatters very easily. It's too brittle. So the steel stops the brittleness, and it also, in terms of compression for like bridges and buildings, steel is not very good for that, but the concrete is better. So it's good in compression, bad in extension for concrete. Steel tends to be the opposite. Okay, so looking at that bit is really common, and that's where most things are nowadays in material science. It's all about the composite materials. So have a look at those, draw some pictures, get some notes. Okay, a little bit of research, find out some good stuff. If you go on the Institute of Physics website and research just by Googling it, but see which ones come from the IOP, then they've usually got some really nice diagrams. Okay, thanks guys.